Welcome to today's tutorial over calorimetry. I'm going to start by explaining heat energy units. You need to have out a calculator, your notes, and as well you need your homework packet. Okay, heat energy units. It says the calorie is a commonly used unit for heat energy. Energy contained in the foods we eat is actually measured in kilocalories or calories with a capitalized C. So for example, it says one Oreo contains 55 calories or 55 kilocalories. So what you're supposed to acknowledge here is that a calorie with a capitalized C is the same as a kilocalorie. So if you have 1,000 calories with a lowercase c, it's equal to 1 calorie with a capitalized C, which is also equal to 1 kilocalorie. So essentially, these are the same. Okay, so you need to emphasize here that if you capitalize a calorie, it's 1,000 times larger than a calorie with a lowercase c. So let's talk about calories for a second. We eat food to obtain calories. Calories are energy for our body to do whatever it needs to do on a daily basis. For us to think, for us to move, for us to even breathe, we need calories. And we get this from the foods that we eat. Okay? Now, if you eat too many calories, you've got extra. You've burned so many doing your daily activities, but you've eaten too many, so you have extra. This extra calories that you took in are stored as fat in your body. So then on another day, say you don't eat enough calories. Okay, so you have a negative amount of calories in your body. Well, your body gets those calories by breaking down the fat storage that you have. So it kind of balances each other out. Okay, we store the extra calories and then we burn the extra calories when we need them. Okay, so another unit that we use is the joule. It says the joule is the SI unit for heat energy. We will primarily use joules in our calculations, okay? And something important that you need to know, a joule is smaller than a calorie, okay? You've got 4.18 joules will equal 1 calorie. And of course, 1,000 joules will equal 1 kilojoule. So kilo means 1,000, remember? So 1,000 joules equals 1 kilojoule. So that's important for you to know the perspective on size. Okay, calorimetry. It says heat that is released during chemical reactions can be measured by calorimetry. The law of conservation of energy states that energy cannot be created or destroyed, only converted into different forms. We apply the law of conservation of energy when we perform calorimetry experiments. Because of this law, we know that the heat released by a system must be absorbed by the surroundings. Okay, and we're going to use this in order to measure how much energy is in a specific reaction or is released during a reaction, or in lab, how much energy is stored in food. Okay, so the equation you use is Q is equal to MCAT. M stands for mass, and in grams. C stands for specific heat, and specific heat is a constant for different materials. So for example, water's specific heat is equal to 4.18 joules per gram degree Celsius. And then delta T. Now, anytime you see delta or this little triangle, that means a change in something. Well, T stands for temperature, so we've got your final temperature minus your initial temperature. Now, we're going to use MCAT equals negative MCAT in our calorimetry calculations. What this means is the heat released by a system is equal to the heat absorbed by its surroundings. Okay, that's why one of them is negative. Okay, the negative sign indicates exothermic because on the left here we have positive, that's endothermic. It says you need the negative sign on one of these sides of the equation to make it equal. One side's exo and the other side's endo, so they have to have opposite signs. Okay, so it's very important that you include that in your calculations. So what is a calorimeter? We've talked about how to do these calorimetry problems, we haven't talked about a calorimeter at all. It says a calorimeter is a device used to measure the absorption or release of heat in chemical and physical processes. The diagram of the bomb calorimeter is here. Now, let's look at this. Okay, we have a bomb calorimeter, and it's made of some material that allows for a very closed system. What I mean by that is this metal that it's made out of allows for very little heat to escape. Okay, so let's say we have a closed system here. And this container is filled with water, and inside of that container you have a reaction chamber. In this reaction chamber, a reaction will occur. So let's say it's exothermic. Okay, so this exothermic reaction occurs, meaning heat is released from the system to surroundings. Well, in a calorimeter, we're going to use a thermometer to measure a temperature change when this exothermic reaction occurs. Because the heat released is going to be absorbed by the water, and then the thermometer will record that temperature change. And by doing the calculations, MCAT equals negative MCAT, we can figure out the energy absorbed by the water, and that will equal the energy released by the reaction. Okay, so your notes say, for calorimetry calculations, it is assumed that the heat absorbed by the water in the calorimeter equals the heat released by the chemical reaction inside the reaction chamber. That's exactly what I said. It's very important to remember that. It is necessary to measure the mass of the water and the initial and final temperatures of the water. So let's look at an example. This is an exothermic reaction between hydrochloric acid and sodium hydroxide was carried out in a calorimeter. The mass of the water in the calorimeter was 150 grams. It's very important. The initial temperature of the water is 25 degrees Celsius. After the reaction was complete, the temperature of the water is 35 degrees Celsius. This is our final temperature. How much energy in joules did this reaction release? The specific heat of water is 4.18 joules per gram degree Celsius. Now, if you remember, our equation is Q equals MCAT. Okay? Now, what I can measure from the information they gave me here is how much energy the water is going to absorb. Okay? So, the mass of the water is 150 grams. The specific heat of water is the 4.18 joules per gram degree Celsius. And the temperature change, remember it's final temperature minus the initial temperature, is equal to 35 minus 25, which gives me a delta T of 10. Okay, so when I multiply all this together, I end up getting 6,270 joules. Okay, let's think about this for a second. This, in which I just calculated, is the amount of energy absorbed by the water. But the question says, how much energy in joules did this reaction release? Well, remember how I said MCAT equals negative MCAT because we assume that the water is absorbing an equal amount of energy that's released from the reaction? The only difference in these numbers is that my answer should be negative. Okay? It even tells me it's exothermic. So by telling me it's exothermic, I know I need a negative Q or a negative H value. Okay? So it needs to be negative because this reaction released energy. Okay. So I want to work a couple sample problems from your homework. Okay, this is the homework page. And let's go ahead and go to sample B. Okay, so I'm going to open a PDF just because I have more room. Okay, sample B is a completely different problem. Okay, we are still going to use the same equation. It's just we're solving for a different variable. Okay, the problem reads, a 200-gram sample of brass at 100 degrees Celsius is placed into a styrofoam coffee cup that contains 200 grams of water at 20 degrees Celsius. Disregard the absorption of heat by the cup and calculate the final temperature of the mixture. Okay, let's think of what I have here. I have this sample of brass at 100 degrees Celsius, so that's pretty warm, right? And it's being placed into this coffee cup with this much water at this temperature. Okay, so what I know is when I put them together, at some point they're going to equal out to a constant temperature. Okay, we call it equilibrium. So I'm going to use MCAT equals negative MCAT to solve for the final temperature that's reached. Okay, so for the left side, I'm going to choose to use brass for the left and water for the right. Now, it does not matter which one goes where. For example, I could have put water on the left side and it would have been positive, and brass on the right side and it could have been negative. As long as the correct values stay together, it doesn't matter which one goes on which side. Okay, so what is the mass of the brass? 200 grams. It's right here in the problem. So I put 200. What is the specific heat of brass? Now, on your homework sheet, it tells you the specific heat of brass is 0.375. And what's the change in temperature? Now, let's remember what change in temperature entails. Change in temperature requires that I have a final temperature minus an initial temperature. Well, my problem only gives me one temperature for brass. That temperature is your initial temperature. Okay, the mixture itself will reach a final temperature. That's what we're trying to solve for. So I'm going to plug in TF minus 100 because that's all I know. I don't know the delta T because I don't have a final temperature. Okay, this is equal to negative. Now don't forget this negative, it's very important. The mass of the water is 200, right here. Okay. The specific heat of water is 4.18. And the change in temperature, again, I only have one temperature, which is my initial. So I'll put TF minus 20. Now, this may look overwhelming at this point. How am I going to solve for TF? It's in parentheses with something else attached to it. Let's try to simplify it as much as we can at first, okay? If you look at both sides, what I have in green and what I have in red, there's something in common. That is that the mass of the brass sample and the mass of the water are the same. Well, I can cancel these out, okay? So you might want to look at both sides, see if they have something in common. They cancel out. Okay, now remember to keep the negative on the right side. That doesn't go away, but the value 200 does. This helps us a lot. It makes the number a lot smaller. Okay, now if you're looking at the green or left side, I have to follow order of operations before I can do anything when you're solving algebra. And the first thing in the order of operations is parentheses. So I've got to distribute this 0.375 to what's in parentheses first, then I can go on to multiply, divide, and do that other stuff. Okay, so 0.375 times TF gives me 0.375 TF. 0.375 TF times negative 100 gives me negative 37.5. Okay, so on the left side, I have 0.375 TF minus 37.5. This is equal to, now what I need you to understand is that this negative goes with the 4.18. Okay, I'm going to distribute that what's in my parentheses. So I have negative 4.18 TF, and then negative 4.18 times negative 20. Okay? When you multiply two negatives together, you get a positive. So this is where a lot of kids mess up. Plus 83.6. So hopefully you're following along with a calculator and doing these calculations as well. It really helps your brain to think through these problems if you're working them with me. Okay? Now, this should look a lot more simple, okay? You should be able to handle this. So what I want to do now is to get the TFs on the left side and to get the numbers on the right side. So in order to do that, first I'm going to add 37.5 to both sides. Okay, so the 37.5 will cancel on the left, and I'll end up with 0.375 TF is equal to negative 4.18 TF plus, and I get 121.2. Okay, next I want to get all of the TFs on the left side. So I'm going to add 4.18 TF to both sides. Now, if you want to combine those two steps I did in red, I am perfectly okay with that. But the first time I'm showing you, I want to do it, I want to show as every step as possible, okay? So then I have a total of 4.556 TF is equal to 121.2. Now this should be easy for you to solve. Divide both sides by 4.556 and you get your final answer, okay? And your final answer for this, I'm running out of room, so I'm going to put it in this corner over here, is that TF is equal to 26.6 degrees Celsius. Okay, so when you put these two materials together, this warm brass sample with the water, it's going to reach equilibrium at 26.6 degrees Celsius. That's the final temperature. Okay? Okay, that's for solving for TF, or the final temperature. Let's try another example in your notes. It's a lot less math, I promise. Sample C. Okay, now sample C says a 100-gram sample of tungsten at 100 degrees Celsius is placed into 200 grams of water at 20 degrees Celsius. The mixture reaches equilibrium at 21.6 degrees Celsius, which is the final temperature. That's the information we wanted on the last calculation. Calculate the specific heat of tungsten. Okay, this time the unknown is specific heat. Hopefully you've recognized that specific heat is this letter C in all of our calculations. So I'm going to set up my calculations. I've got MCAT is equal to negative MCAT. I'm going to plug in what I know. I'm going to say the left side is going to be tungsten. And the right side is going to be water. Okay. So the mass of the tungsten, I know what that is. It's 100 grams. I don't know C, which is the specific heat. That's what I'm trying to figure out. Now, I do know delta T this time, which is nice, okay? They gave me that final temperature, and I know the initial temperature. So remember, it's final minus initial, so it'll be 21.6 minus 100. So yes, I'm going to get a negative temperature here. It'll be negative 78.4 degrees Celsius. Okay, this is equal to the mass of the water, which it tells me it's 200 grams. The specific heat of water, 4.18 when it's a liquid, and it is in this situation. And the change of temperature, I know that as well, because the initial temperature is 20, the final is 21.6. So remember, it's final minus initial, 21.6 minus 20 gives me 1.6 degrees Celsius. This is a lot more manageable than the last problem that we did. Something I forgot to do was to put my negative. Don't forget that. That is the easiest thing to forget. One side's positive, one side's negative. It will mess up your entire calculations if you don't remember to do that. Okay, so I'm going to simplify on the left side by multiplying everything together, and I get negative 7,840 C is equal to, remember, negative 78.4 times 100 will give me that, is equal to all of this stuff combined. Now remember, it's going to be negative because of this negative symbol. So when I multiply, I get negative 1,337.6. Easy enough to solve for. I just divide both sides by 7,840. Don't forget, it needs to be negative. Okay, your signs are very important. And I get C is equal to 0.171. Now the unit for specific heat is joules divided by grams degrees Celsius. Okay, and of course if you want, you can check your work by plugging this number in to C and seeing that both sides equal out. Okay, so if you want to check your work and make sure it's absolutely correct, go for it. Okay, so hopefully this tutorial helped you understand calorimetry questions a little bit better, and you're able to do tonight's homework a little better and tomorrow's lab a little bit better. If you need extra help, there should be more help on the website. Okay, and the website is, of course, www.academicchemistry.pbworks.com. Okay, have a great day, and I'll see you in class tomorrow.